So the whole installation contains the following equipment. We have here the power, the mains, so-called mains. We have the main switcher, after that an auto transformers, and 3 types of loads. We have the resistive load, which is adjustable. With this switcher, we can insert practically 4 such resistors. We have here the coil, adjustable coil with an adjustable inductivity. One can insert an iron into the coil in such a manner that the inductivity of the coil is adjustable, becomes adjustable. And finally, we have a capacitor here. All these elements modulate cable and different power plant elements. And here we have a switcher which provides us the possibility to have an inductive resistor load or a resistor capacitive load. Yes. This voltmeter indicates us the value of the adjusted by the auto transformer voltage. And this can be correlated with the apparatus indication. And of course also we have here, we can adjust the current, can make the value of the current greater. Okay, now we power up the entire installation. That means that practically we have to set up 100 volt approximately, okay, something like that. We watch here very carefully in order to reach the root mean square value. That means practically that the voltage is very precisely established to this certain value. After that, first of all, it would be better if we sum up the whole installation. Practically, we have the power source, which is an auto transformer. After the power source, the energy is distributed to 3 different loads. We are talking here about this resistive load, which is practically provide us a power factor of 0. That means a cos phi of 1 unity, not the power factor, but the phase shifting between voltage and current is 0. That means a power factor of unity. After that, we have here the coil. It is an adjustable coil, which is inductivity can be adjusted in the large scale area. And finally, we have also a capacitor. This measurement instrument is a typical single-phase power quality instrument that provides us the possibility to measure different electrical parameters. That means with this current clamp, we measure the current, all the parameters of the current, and with these clamps, with these crocodiles, so-called crocodiles, we can measure the voltages. Here we have only the voltages because we don't have any load, and in order to measure the load parameters, first of all, I set up only the resistive load. That means I have to insert into the circuit 2 resistors. That means we have established a current value of 1.1 amps. After that, we can not only visualize the waveform, and one can immediately notice that the phase shifting between these 2 waveforms is 0, a power factor of 1, which is I already mentioned, and now we can see that very clearly. And this power quality instrument provides us the possibility to measure other power quality indicators, such as one can see root mean square value, THD, total harmonic distortion, crest factor, and many other parameters, which are to be seen very easily once we push this button, which provides us to switch between different parameters. And here, in red, we have the voltage parameter, the maximum value, the average value, the minimal value, the peak, the peak positive value, the peak negative value, and also we have here the amps, the same parameter, almost the same parameter for the amps. One can notice that even for a root mean square, for the current of, let's say 1.8 1.1 amps, we have here a maximum value of 1.5. Similarly, in the same manner, we can reach for the voltage 139. That is to be underlined that practically the voltage, the maximum voltage is not the voltages indicated by the most of the power instruments, which is the root mean square value, but the maximum value. The relationship between the maximum value and the root mean square is this, that, of course, for this type of signal, which are sinusoidal signal, the maximum value is square 2 multiplied with root mean square. Furthermore, we can show, we can see different parameters, which is power, mainly, basically, power quality indicators, RMS, DC, so root mean square, direct current component, total harmonic distortion, crest factor, flicker, and of course distortion factor in percent. Also here we have the connection schematics, yes, and this is only for this button which provides us all these parameters. Once we also have to measure the powers, all kind of powers, we have active power, reactive power, which is practically 0.8. So since we have only the resistors, one can ask why do you still have such a reactive power? Because these resistors are not merely ideal resistors, yes, doesn't exist such things. They are also designed, so manufactured by some sort of conductor which is coiled, and that's why we have some little small reactive power, of course, inductive because of the coils. Correspondingly, one can measure also the apparent power, which is the apparent power, the power factor, the distortion power factor, tangent phi, and phi sine phi. It is practically, as I already mentioned 2 times already, is 0. On the other hand, one can ask if these waveforms are purely sinusoidal. Not only that they are sinusoidal, as we can practically see here, the instruments provide us the so-called Fourier decomposition of the signals. That means we have here this button, once we push this button, we have for the voltage and for the current the Fourier spectrum. And we have here, we can move here, for instance, to see the fundamental component and all other component. Because of the symmetry of the waveforms, dominant are only these even harmonics. I mean 3, 5, 7, 9, 11, and so on. This instrument can measure up to 25 such component of the Fourier decompositions. In this case, because we have here a resistor, only the fundamental is the dominant component. It is very important to understand this knowledge, because once we have the energy provided, for instance, in a photovoltaic plant, from the inverter to the network, it's very important to measure and to preserve these parameters of the alternating current waveforms. Once we have this, we can furthermore inject into the network, because the basic idea of photovoltaic plants is to provide clear green energy starting from the panels to the inverter, and after the inverter in the AC side to inject into the network. And this kind of injection is only possible according to the network regulation or the grid restrictions. Only we have these waveform parameters in terms of their pure sinusoidal and no other harmonic pollutions. That's why it's important to measure, and in this way we can characterize, we can measure the performances of such inverters. Furthermore, I want to show different loads. I not only insert the resistors, but also I'll try to insert also the inductive. Once we can notice that the current jump up to 2 amps, the 2 amps, this is the current. Yes, of course the voltage remain merely the same, but more important is the fact that we have a phase shifting here. One can notice that the waveforms are not with no shifting. They are practically the circuit, we can say that is a lagging circuit. Similarly, we can measure different parameters. Yes. And one can see that the current can jump up to 3 amps. Its average value is 2 amps. Of course, average sinusoidal value. And we have here also similar parameters. Here we can measure the powers and the most important difference between the prior measurement, it is that here we have the reactive power, an amount of 150 var inductive. So it's not so small like it was in the previous experiment, because here we have inserted a coil whose inductivity is also could be adjusted. In adjusting the inductivity, we can inject into the network reactive power of inductive type. As we should know, there are two types of reactive power. It is inductive reactive power, which is provided mainly by coils, such as motor, transformers, and other devices that are to be found very high into the network, because the incidence of such equipment is very large nowadays, because they are the main power supply into such a grid. And in modern grid, we have also these photovoltaic plants, wind plants, and other kind of distributed energy plants, so-called distributed energy plants, which have to properly interact with the already existing network. And the idea is to, again, to preserve the parameter and the fundamental issues that the grid impose. We have to adapt to the grid. Regardless the amount of power we want to inject into the network, we should, again, have the same grid parameter in terms of voltage, in terms of frequency, and other power quality equipment. And finally, I want to show you also, here we have the harmonic spectrum, which is very similar. And for the amps, it's also the same. Okay, and now again, we want to insert a capacitor into the network. Okay. Now we can see that the waveform, it's not only it is leading, is shifted, but it's also some sort of distort. It is because the capacitor is not practically an ideal capacitor. Ideal cannot provide a pure permittivity. That means that the dielectric of the condensator cannot be an ideal one. It's very difficult to achieve such a performance, and that's why one can notice this small distortion of the current waveform. But on the other hand, we have also the same voltage, the current is less, because the capacity of the condensator is not so strong. It practically modulates the cable capacity. Once we have, after the photovoltaic plant, so in the network where the photovoltaic plant inject energy, we have a lot of cables, and these cables, among resistivity, among resistance, they also exhibit capacity and inductivity. And the capacity is modulated by this simple merely condensator. One can notice also the power, and we can see immediately here the symbol, the type of the capacitor, which means that this reactive power is not anymore inductive one, it is a reactive one, capacitive one with minus. This is could be a very big problem in large power plants, because there are a lot of cables of different dimensions, a lot of cables that exhibit a lot of reactive energy, and this reactive energy is to be managed in order to preserve the parameters of the network. You know that the reactive capacitive energy, this kilovar, determine a limitation of the active power injected into the network, especially during the night time where the power plant does not operates and it is already on grid. Practically, the power plant becomes a capacitor. A capacitor that consumes this kind of energy, a capacitive energy. We are talking here again about large power plants that are constantly connected to the network. And they are seen during the night time as a large capacitor. And this capacitive reactive power is to be compensated. There are two kinds of compensation, of capacitive compensation. One is to set up the inverter of the photovoltaic plants in such a way that they operate in an inductive mode, so antagonist mode as the capacitor. In this manner, they annulate each other. They practically the complete reactive power becomes zero. Or there's another possibility to use such a inductors, which are connected only during the night with such a night sensor, and they are activated during the night around, I don't know, in this time of the year, I think it around 9 o'clock. They activate, they insert the coils, and in this manner, this energy, this reactive energy capacitor, reactive energy is compensated. And this kind of compensation provides us clear energy and clear power quality indicators. One can notice also the current and the voltage. Yes. Okay. And the reactive power and this waveform. In order to get rid of these ripples, it is very difficult in the real installations. This distortion becomes more aggressive and can provide a lot of power quality issues. And most of the unfavorable consequence is that some power equipment, protection power equipment, can trip without any reason. And the operator and the network provider do not know the cause of this tripping of the protections, and this tripping is due to this specific current waveform. So there are a lot of technical issues which are to be considered when we are exploding such a power plant, especially the large power plants, because nowadays we do want to create clean energy, so I mean carbon-free energy that can save our nature and so on, but in the same time we have to consider the electrical problem issues that are generated by these new green energy sources. And we are talking here about the photovoltaic plant, so-called PV plant, because they are the most cheap, they are cheapest, they are easy to use, and can be adapted to any load, to any consumption graphic, to any consumption curves. For large power plant, which is nowadays the case because everyone wants to replace the old power plants with these photovoltaic plants, which more or less are cheaper. For instance, they say that for 1 megawatt is necessary 1 hectare, and in terms of financial needs, for 1 megawatt it's almost 1 million euro. It sounds a little bit high, but this investment is rather rapidly recovered after a few years, and the plant, its lifetime, it's around almost 20 years. If the maintenance is properly performed, if the equipment are new when the plant is installed, and everything is very tight monitored in terms of power quality, in terms of mechanical maintenance, in terms of everything that needs to be kept in proper parameters during its operations.